Those here. Good. All right, just going to be part. All set.
Okay, so welcome to this last morning session today before the lunch. I'm sorry for the confusion since the programs set on one side 11 and on one side 15. Now we have 11:20, but that's okay. That makes the lunch break a bit more efficient. And the first speaker today is actually from our group in Erlangen. That's Gaurav Nath, and he's talking about reaction limited evaporation for color gradient.
Right. Thank you, Dr. Hatting, and I welcome you all here. So the topic of my talk is how to do reaction-limited evaporation for the color gradient multi-component model. This is mostly a method development talk, but I'll talk about some potential applications towards the end. The first slide never works. Thank you. Yeah. So the color gradient multi-component model is a model made specifically for immiscible fluids and therefore commonly used to study flows in porous media. The advantage the color gradient model is that you can independently tune the model parameters. So the surface tension, interface thickness, density ratio, viscosity ratios, you can tune them independently. And you can go to higher density ratios and viscosity ratios. And the fluid interface that you get in this model is quite stable and consistent. However, the color gradient method does not have an inherent method of evaporation. Compared with the pseudopotential method and the free energy method, they can quite easily do the diffusion limited evaporation. It's inherent in those models. The color gradient model does not show similar diffusion limited behavior because it is made for immiscible fluids. It does not allow the partial solubility of one fluid component inside the other. To add to that, the color gradient, the equation of state does not account for phase change, right? So keeping in mind the limitations of color gradient with the diffusion limited evaporation, I propose a way to do reaction limited evaporation with this model. Evaporation can take place in different regimes depending upon the limiting mechanism. So in reaction limited evaporation, the evaporation is limited by the transfer rate of molecules across the liquid vapor interface. In contrast to diffusion limited evaporation, where it's the diffusion of vapor molecules away from the interface, that's the limiting mechanism. You expect to see this reaction limited evaporation when you're evaporating into a vacuum, into a pure vapor phase, or when there's a gas draft going across your or over your fluid liquid interface in that case. These are some of the prominent examples. You can use something like the Hertz-Knudsen theory. This comes out of it's based on the kinetic theory to model the evaporative flux in reaction limited evaporation. And this has been used successfully in both experimental and theoretical studies to model this flux for the past many, many decades. So for a given surface and an evaporative flux, the total mass loss rate in reaction limited evaporation is proportional to the surface area. Here, the flux phi I'm assuming to be a constant, right? So we want to achieve the same thing in lattice-Boltzmann, but in lattice-Boltzmann, our interface is diffused. So each of these pixels you see is essentially a lattice site. We need to find a way to remove mass from the lattice sites in the interface region so that it's consistent with what reaction limited evaporation should be. So we can assume that at each of the lattice sites, we have some elementary volume with the lattice spacing, and the rate of mass change in this elementary volume is this due to some net flux phi, is this quantity. And if we sum it up over all the sites in the interface region, we would get a total mass loss in lattice-Boltzmann. However, this simply won't be equal to the continuous case because it's a diffuse interface and that's a continuous one, right? So we need to account for this somehow. Here I introduce a real valued constant that I'll call the discretization factor. It accounts for the fact that I'm trying to represent a continuous interface as a diffused one, and that is also discretized on a lattice. What exact value this S will take, I'll talk about in the coming slides. Equivalently, we can also say the rate of mass change due to flux at each of the sites can also be due to a mass sink with the falling rate. And I can rewrite the above equation like this, and comparing the last two relations gives me this important relation. This essentially relates the evaporative flux you want to model with the mass sink rate, and this is the rate at which you would end up removing mass from the lattice sites in the interface region, right? But this is derived under the assumption that the evaporative flux is constant across the entire surface. So keep that in mind. Okay, the next important question is, how do you select the sites at the interface? So in the color gradient model, you have this parameter called the color gradient. This is a vector. And here I'm showing you the magnitude of this color gradient vector. So this is for a spherical interface, the same thing you saw in the last slide. It has a value of 0 in the bulk regions and goes to some maximum value across the interface region. So it becomes quite obvious that you specify a threshold, this parameter, this is a constant, and all the lattice sites which have color gradient magnitude greater than this, you choose for as evaporation sites. So this is quite easy in this method because you already have the color gradient. This method is quite cheap and local. The color gradient is a non-local thing, but you already have it. So you don't need anything else making it local. Only one threshold is actually needed. That's this one that you need to tune. And this also works for density contrast. So it's quite obvious that the threshold parameter that selects the sites at the interface and the discretization parameter are connected. In fact, they have to be chosen together in tandem. So this is the equation I showed you earlier. The threshold basically changes the sum, that is the amount of evaporation sites you select at the interface, right? And this is the discretization factor, which you must also choose so that this side becomes equal to that side. So this is what we're trying to do here in this case. So to make things easier, I told you earlier, this thing is essentially a real valued constant. Doesn't matter. I assume it to be a natural number constant. And I just tune the value of threshold, that is this sum, so that both of these things become equal. So to be honest, this is the threshold is the only free parameter you need to worry about. The effect of S I can show you here. So as I say, I assume it to be a natural number constant. So this is for 3, 2, and 1. You can see when S is 3, you see it can roughly be interpreted as the number of layers of evaporation nodes that you have at the interface. I use 3 for my study, and I won't advise you go to 1. With 1, you can end up with the problems that you can have holes, and you are not uniformly covering your entire interface. So 2 is also a valid approach, but 3 is what I will. Now I show you the entire algorithm, which also would explain to you how I'm doing the mass exchange and all. So the evaporative flux that you want to do, you've determined the mass sink rate. Delta X is the lattice spacing, which is 1 in this case. The discretization parameter you fix at 3. So you have your mass sink rate. You choose a given value of threshold. This gives you the evaporation sites. At the evaporation sites, you basically exchange the mass between the two components, right? So here I'm doing it with the resting populations. I remove some mass from the resting populations of one fluid, give it to the other at the evaporation sites that I've chosen in this case. So this method is globally mass conserving. This is not really a unique way of doing it, and I'm not doing anything special here. I'm simply readjusting the amount of the red fluid density and the blue fluid density at the site, but the total density does not change. Then you determine your microscopic variables, that is individual component density, which would change because of the exchange I just did. Total density won't change. The combined distribution. So the color gradient function, what it does is, even though you have a distribution function for every component, the main algorithm, that is this, is done on a color blind distribution. You just combine all the distribution functions together. This is this one. So what I just did does not really affect the color blind distribution. So the effect of this exchange is not really felt in the collision step. It only comes in the recoloring and the perturbation step. Then you do your streaming. I'm not really explaining you the core of the color gradient algorithm because it does not matter. What I do does not really change the core of this algorithm. So it can also be applied to other variants. So the obvious question on your mind is that you would have to tune this threshold every time, right? So I'm going to show you for different shapes of the interface, how does this threshold value varies and how much accuracy you can actually get. Does it depend upon the size of the interface? If I increase the size of the interface, do I have to retune again? And how does it, what is the accuracy with different evaporation rates, faster, slower in that case, and some special case in this case. All cases are run with these parameters. This is the interface thickness. I choose it to be the sharpest as possible, but it also works if you increase the interface thickness. What I'm going to do is I'm basically comparing the interface position during evaporation between my lattice Boltzmann simulation and some analytical solutions I have for different shapes of the interface to find the optimum F and show you the accuracy. So finally, I'm on to the results now. First, I start with a flat interface. This is a pseudo one-dimensional domain like this. I initialize some amount of red fluid. This is the evaporating fluid, and the remaining is the blue fluid in this case. In this case, the analytical solution simply gives you how the height of this red fluid evolves over time for a given evaporative flux. This is the time for complete evaporation. So I'm basically showing you a comparison of height as it evolves over time between the analytical solution and the lattice Boltzmann solution. So in the lattice Boltzmann solution, I'm showing you 3 different evaporation rates. This is actually quite fast. So these are in lattice units, and this is an interface speed of approximately 3 lattice units per 100 time steps. It's moving quite fast. And this is then 2 orders of magnitude smaller in this case. So if you choose your threshold correctly, in this case, so I have chosen this value, you can get a very accurate result. So at about 50% evaporation, less than 1% error, and towards the end, I'm getting about 4% error. The error increases because as you go towards the end, the height of the interface remaining becomes comparable to the interface thickness itself, so the results becomes unphysical. So I do not report results after this. What you see is you have good agreement across a wide range of evaporation rates. If, just for comparison, if I change the threshold value slightly, so this is the pentagon that you see in this case, it also works quite well, but you see some error at the end. So you see what is the effect of changing the threshold in this case. And I choose this threshold because this is the one I'm going to keep common across all the shapes that I show you now. Now we have a spherical interface. So this is a cubic domain. I initialize a sphere of the red fluid surrounded by the blue fluid in this case. And I do the same thing. This is the analytical solution. And this is the analytical solution taking into account the equation of state of lattice Boltzmann. So what happens is when the droplet radii becomes smaller, that is the curvature increases, Laplace pressure increases. In lattice Boltzmann, pressure and density are connected, so density will increase inside the drop. And you can take that into account in the analytical solution as well. So these are the 2 differences. What you can see in this case that this difference only comes in towards the very end when the drop radius becomes significantly smaller. At higher radius, you don't really see the difference, but I show it for reference in this case. I show you the same evaporation rates again, this value of threshold. This is the one we showed last time, but as a reference, again, I see a good comparison. That's proper evaporating. And these are the errors you see in this case. So fairly acceptable across a wide range and size independent. So this was done for a 128 cube study. I doubled the size of the domain, double the size of the droplet, keep the threshold the same. It works even better now. So this threshold I show you is essentially independent of the size. Then we have, in this case, hemispherical drop on a substrate. So now you have walls on the top and bottom. These are neutrally wetting. The analytical solution remains the same as last time. So this is, interesting. In this case, you'll see that I get good, so this is the same threshold as last time. I get good agreement if I evaporate slowly. I get slightly irregular behavior if I evaporate too fast, which is understandable because this analytical solution assumes that the shape remains hemispherical throughout, but if you evaporate too quickly, the local contact angle deviates from 90 and the shape deforms out of hemispherical a bit. That's why you don't see this error if you move slowly. And you did not see this error in the previous cases where there was no wall. But again, you see, and even with this thing, you'll get up to under 5% error, and this error usually happens towards the end. Good agreement. Again, this is a case run on a slightly bigger grid for the same threshold. It performs even better in this case. This is another case that is spinned spherical cap. So I'm spinning a droplet on a cylindrical cavity in this case. So this is the equilibrium drop profile. The drop profile is essentially pinned on the outer edge of this cavity. And then you evaporate it like this. So this is my best effort to pin the droplet. However, in lattice Boltzmann, for those of you who know, even if you try to pin the droplet, the contact line would still move very slowly. It is still moving. So eventually you'll see it still gets here, and after a while it goes down in the channel, right? So at this point, when it gets to the inner edge of the cavity, I have to, stop reporting the solutions there, because I'm actually comparing the height of the droplet. The height of the droplet is measured above the cavity. If it goes below, no point anymore. So I'm comparing the height as it evolves. In this case, this is the point of unpinning. And for this threshold that I used in the previous cases, you see you get the following error. Yeah. So I show you the error at the data point just after unpinning, so about 7 to 8% error, right? So you have to understand that in this error, it's included the fact that in the analytical solution, you assume that the contact radius is fixed, does not change. Well, in this case, it does drift a bit. So some error is understandable here. And for all the cases I've shown to you up till now, I've been using this same value of threshold. For some case, if you do not want this error, you can further adjust the threshold and get a much better answer. So my main point here is, for all the interface shapes that I showed you today, this had no curvature. The curvature in this case increased with evaporation. In this hemispherical case, the curvature also increased with evaporation, but this was the constant contact angle mode evaporation. Contact angle was 90, the contact radius reduced. The pinned spherical cap case, where the contact radius was fixed and the contact angle changed. And in this case, the curvature decreased. So it covers a decent amount of range of shapes. For the same threshold, you get these errors. Here I must point out, the upper range of these errors is usually found at the end of evaporation, where the height of the interface becomes comparable to the interface thickness. So for most of the duration, the error is comfortably under 5%. This I can say quite confidently. And the main point is, if you have a given set of CG model parameters, so some interface thickness, some density ratio, some value of surface tension, you have to do some of these benchmarks to tune a value of threshold. And this should work for a general shape of the interface with some reasonable error. I understand I've not covered all the interface shapes because these are all the positive curvature shapes. There are other shapes out there, but I'm quite confident that if you just tune this once for a given set of parameters, you can achieve accuracy comparable to the analytical solutions. This is a special case. So in the cases I showed you up till now, the flux really did not change across the droplet. This is supposed to mimic the case where the drop evaporates from a heated substrate. So more flux close to the substrate than on the top. And this flux also changes with time in the sense that when the droplet becomes small, the flux becomes more or less uniform. So it's basically based on this expression. This is expression in most theoretical studies that do this kind of stuff, they assume. If you try to compare the answers, quite obviously, Lattice-Boltzmann agrees well when the flux does not vary as much from the top to bottom. So this is the ratio of the max intervening flux. I feel like if you go to 3, this is the absolute limit of the method at the moment. And you can further reduce this error if you refine the resolution of the drop. I get that. But for weakly varying fluxes, so when the flux varies like 2 to 3 times across your interface, you can still get away with reasonable amount of error. I'm saying this because the formulation I made, I just assumed the flux was constant. But the other important stuff is for practical values, the value of this K is usually of the order of 1. So the flux in the case of liquids like water and isopropanol does not actually vary that much in reaction-limited evaporation. So this brings me to the conclusion of my talk. I proposed a way to do reaction-limited evaporation. To my knowledge, this is the only formal way of doing this. This method is local, does not have any computational overhead because color gradient is already there, doesn't do any change to the core algorithm, should work for other color gradient variants. And I say for a set of CG model parameters, a single parameter needs to be tuned so that you can now have accurate results. I showed you unit density ratio results at the moment, for which a single threshold works for general shape of the interface over a wide range of evaporation rates, going from pretty fast to quite slow. Applications for this are the isothermal reaction-limited evaporation. So in this case, you have, for example, drop evaporation under the flow of a neutral gas. These guys already tried that, so they have drop evaporation for pillars, and there's a fan next to it that blows wind over it. And they were able to compare the evaporation rate with the flux predicted by the Hertz-Knudsen theory that I showed you in the start. So you can use a similar thing to do this kind of stuff. Also, if the flux varies weakly, you can also use it for non-isothermal reaction with evaporation. That's drop evaporation for heated substrates, where for fluids like water and isopropanol, the flux really doesn't vary as much across the surface. So with this, thank you for listening. I'm open to any suggestions. Thank you.
Everybody, next speaker is already setting up. You have time for a few questions?
I might have missed it, but why did you plot everything in log?
No, I plot everything in log because if you plot things linear, you don't see this small error. You think everything works. You have to choose just to get the, like for stuff like this, you won't really notice that there really is an error if you just plot in linear. Everything looks fine. But if you,
This becomes a bit.
but that happens at the end.
Yes.
Just
So, second question, I'm not sure I understood, but did you show a 3D simulation?
3D. And the slope thing I checked. No, so no. So the slope I checked in a separate simulation. So as I said, the mass loss rate has to be proportional to the surface area. This I checked separately that the mass loss rate in my case is proportional to r squared for a drop. This I checked. I'm not showing that here, but that's no, it's not here actually. It's not here. I checked that separately. You mean with this one? 3D. No, this is the analytical solution of the height of the drop. Yeah. No. How do I? The mass loss rate is proportional to area, right? Therefore, the height should be linear. Think about it. Think about for a sphere, for example, mass loss rate is proportional to r squared, right? So the radius should be linear. This is a well-known result. This I can show you. You understand what I mean? For diffusion limited evaporation, it's the opposite actually. There, it's r squared that varies with T. So there is a difference in evaporation rate. The scaling difference is there. That's why I stress on the fact that there's a difference between diffusion limited and evaporation. Yeah.
Does your evaporation rate depend on the viscosity of the liquid?
Not at all. Like in terms of accuracy, nothing happens. You can change any. You can change the viscosity ratio. I've tried that. It won't affect the result. So this is basically because the color gradient model is quite robust in that way that you can independently tune these parameters. Not a problem. This is quite simple. This is just no slip neutral wetting on the bottom. It's periodic everywhere else. So that's the thing. You are thinking in terms of diffusion limited evaporation in this case, right? This is mass conserving. I'm just simply converting the red mass into the blue mass. There is no escape here. Okay. There's no flow of vapors if you think about it.
I didn't follow you at the very beginning. So if I understand this question very well, I think this analytical solution is defined based on the open system, not the closed system.
It doesn't depend on that. So you're thinking in terms of diffusion limited evaporation, thinking that it builds up. Oh, no, you're right. It's based on an open system.
Yeah.
Yeah. The thing is, I'm not doing exactly what they mean by in the reaction evaporation. For them, it would be a sink. I'm not using a mass sink here. I'm basically just recoloring the red into the blue. Yeah, but if you can do a non-mass conserving version as well, then you would have to need a sink, right?
Okay.
Yeah.
In due time. Thanks again, Carl.
Hello, good morning, everyone. It's my pleasure to take this presentation. The topic of my presentation is post-field study on evaporation of porous media considering conjugated heat transfer. Then my presentation includes 5 sections, and the first section is the background. Now, heat pipe is a passive heat transfer device. It works as this finger. Based on the pressure change, the heat can be moved from the evaporator section to the condenser sections. And based on the body force or capillary force, the working flow, the cycle can be repeated. So it has the advantages of high efficiency, passiveness, complex structure, and so on. And the left finger shows the various working flow that can be used in the heat pipes. In the yellow box, various incrementals are shown which can be used in the high temperature heat pipes. And this finger shows the various heat transfer limitations, which prevent the thermal load to increasing. And now the heat pipe has been applied in the electronic device and a building, a heat exchanger, aeroplane, nuclear reactor, and so on. But it's still faced with some challenges, such as local overheating, some temperature fluctuation, entrainment, and weak structure sections. To solve this problem, which required us to understand the underlying mechanism of evaporation and capillary transport of porous media at porous scales to obtain high heat transfer rate, obtain high permeability, avoid the drought of porous media, and design and optimize the weak structures. So we select the typical structures inside the heat pipes as this to investigate the evaporation process. Now the next is methodology. We use the cascade lattice Boltzmann method to simulate the follow field, and use the finite difference mass to obtain the temperature field. And for the follow field, the multi-pass procedural potential models are used here. The details can be found in this paper. And the interaction force and gravitational force can be is being considered. And we use the square root scheme for the shield potential. And for the contact angle and the contact angle hysteresis, we use the geometric contact angle hysteresis system. And the details is shown in the papers. And then is for the energy equations. The dissipation term is neglected in our system, in our simulations. Based on the research of John, the second equation can be obtained, in which the latent heat can be adjusted. To solve the energy equations, further Rokota method is adapted. In order to improve the numerical stability, we adapt the variable temp depth to by judge the error during the simulations, and the PR equations of state is adapted to couple the flow and the temperature field. The next section is the verification and the validations. Firstly, we verify the Laplace law and the D2 law. The computational setup at this finger, all the boundary is periodic, and the droplet is set in the center of the domain. For the first finger, you can find the temperature difference increase nearly with the dissipation of the radius. And for the second one, the ratio of diameters decrease with the time. And then for the conjugated heat, the left case we set the heating block at the working floor regions to by comparing the Nussel number, can find the simulated result is consistent with the experimental model with the error of less than 5%. And for the second case, we set the heating region with the five lattice lengths at the bottom to generate a bubble. By comparing the period and the diameters of bubble departure with the experimental model, we can find they are agreeable with each other. Then we simulate various contact angles from 15 degrees to 140 degrees, and the spurious velocities is less than 0.0448. And we compared the pre-described contact angle and the method contact angle by the R code and the image software. From it can be found that the deviations among them is less than 5 degrees. Next, we verify the contact angle hysteresis. The computational setup as that fingers. Droplet is set as the bottom plate, and the top plate can be moved from the left to right. We set the advancing angle is 140 degrees, and the receding angle is 10 degrees. With the different capillary numbers, we can find the shape of droplet are consistent with the previous research. It's kept for the capillary of 1.5. This is called by the geometrical contact angle scheme is not suitable for too small or too large contact angle. Then is next section is rods. This figure shows our computational setup. The left and the right is the periodic boundary, and the top boundary is the constant pressure. We use the equilibrator extrapolation scheme, and the thermal gradient is 0. And the top boundary is heat flux is applied. And for all the wall surface, bounce back scheme is applied. And the properties used in our simulations are listed here. Firstly, we compared the evaporation and coupled temperature field or coupled temperature field. From this video, we can find the evaporation process are similar with each other. But compare the evaporation rate, we can find the evaporation rate with uncoupled temperature field is obviously higher than the coupled temperature field. Then we compared the energy and mass variation. For the mass, we can find the outflow mass is equal to the system mass variation. And for the system, we consider the internal energy, gravitational potential energy, and the kinetic energies. The outflow energy is equals to the system energy variations. And it can be found that the system energy that always determines the internal energies. The gravitational and potential energy and kinetic energy can be neglected. And then we investigate the effect of contact angles. For small contact angles, we can find the capillary effect is obvious. But for hydrophobic surface, the liquid vapor interface receding layer by layer. And for the evaporation rate, we can find for all the case, we can find with larger contact angle, the evaporation rate is higher obviously. That is called by the Kelvin effect. And next, for the effect of heat flux, we can from a video we can find once the heat flux is higher, the top bottom of the plastic media is drying. And then compare the evaporation rate, we can find in the beginning the evaporation rate gradually decreases, and for all the different heat flux they are so close. But once the saturation is less than about 0.7, the effect of heat of the place increase the evaporation rate, and at last once the plastic media is drying, the evaporation rate is reduced to 0. And then we consider the contact angle hysteresis as this one. We set the history windows as 30 degrees. From that, the video we can find the evaporation pattern are similar, and the evaporation rate is so close. And next is this figure shows the rest case, and by compare the drying time for the hydrophobic surface, contact angle hysteresis obviously increase the drying time, which is consistent with our above result. But for the hydrophilic surface, the contact angle hysteresis increase the evaporation rate. I think this may be caused by the smaller contact angle, which increase the liquid vapor interface areas. And the last section is the conclusions. The evaporation rate with conjugated heat is lower than without conjugated heat, but the evaporation patterns are similar. The evaporation rate is higher for larger contact angles. The capillary effect is more obvious for smaller contact angles, and which lead to different evaporation pattern. Heat flux enhances the evaporations, resulting in drying in the bottom of pulse media. The evaporation process with and without contact angle hysteresis are similar, and the contact angle hysteresis has slightly effect on the evaporation rate. That's all. Thanks.
Questions?
You probably said that, but I'm not sure I got it. How do you model the evaporated cooling?
How do you model what?
Evaporated cooling.
Evaporation cooling?
Yeah.
What is what?
I think they included is the potential model. If you saw the temperature field.
Yeah, but you have to some energy dilation, right?
Yes.
That you have to use. Right?
Yeah, the energy equation with the latent heat. So it is,
Yeah.
it is included.
I was just wondering what the latent heat equation looks like that you use.
Maybe look out.
Okay. This one? Okay. This one? Oh, oh. Okay, sorry. This one, yeah. Static gravity is a word between the liquid and vapor, so use this.
So what's the HFG?
Latent heat of evaporation.
Okay. How do you get the HFG out of your
We set it the content, no, but just content. Don't use the properties. We set it the content.
because it does not come out of the equation of state of the period?
What?
It is decoupled. It can be from the equation of data. Here, I think it's decoupled.
Okay, so it's not self-consistent, it's just a number that you put in. Okay.
Yeah, so I think you made the comment that the role of hysteresis is quite small. But I think this is because the geometry that you've chosen, the motion of the interface is only in one direction. So I think it's probably not critical. But you could also, I think I can imagine that if you have geometry that is a bit more random, you might get a phenomenon like Haynes jump, and then you will actually have the interface advancing and receding at different times. Then maybe you will actually see that hysteresis is important. So I wonder if you look at that sort of geometry that's more complex and less regular.
What? Okay. Okay. What can you temperature? temperature difference. This? Also. This one? What? Can you repeat it? Yep. Good.
Okay,
Thank you.
thank you again.
Look pretty good. All right.
Okay, yeah, so thank you, Professor Harting. Yeah, I'm Michael. I work with Professor Kusumat Maja in Durham University, soon to be Edinburgh University. And today I'm going to be talking about evaporation on corrugated surfaces. So first, I mean, given that we've had 2 talks on evaporation, this might not be necessary background. But the main thing I want to talk about here is that evaporation is basically a natural phenomenon where molecules of liquid are escaping from the surface of the liquid. And this is in the case of diffusive evaporation in competition with recondensation of the molecules. So if you have vapor surrounding your liquid, you have to think about how easy it is for the vapor to escape around the interface and whether it can come back and recondense and slow down the evaporation rate. And the reason we're sort of looking at this is there's a number of interesting problems. So one of these is porous media, drying of porous media, which we've already had 2 talks on. Another one is film formation. So if you have a drying liquid on a surface, you want to be able to maximize the evaporation rate to be able to apply coatings to the surface. And then the last one that we're sort of interested in is regulating lubricant depletion on liquid-infused surfaces. So I think Liam showed these sort of surfaces in his talk where it's very easy for droplets to slide off of them. But the sort of application we're interested in is carbon capture. So people are designing these surfaces where you have a reactive liquid infused on a surface. And this will react with the carbon dioxide to capture it, but it's very volatile, so it will evaporate very easily. So we're trying to find ways to minimize the evaporation rate, basically. Okay, so here's a structure of what I'm going to talk about. Basically, I'm going to provide some background information that's kind of necessary to understand how these complex different geometries will affect the evaporation rate. And I'll show the system we're investigating, the method we're using, and then just a few results, and then sort of the future direction we're going to be moving in. So we've already had a talk today on this, I think what I call it kinetic limited evaporation, but on rate limited evaporation, where the evaporation rate is just limited by how quickly the molecules can escape from the surface of the liquid, basically. And this will just scale with the interface area, basically. So the more area you have, the more surface you have for these molecules to escape off. But the case I'm looking at is this diffuse limited evaporation, where, okay, now let's say we have some gas surrounding our interface. The molecules that were coming off the liquid will now collide with this gas, and sometimes they will bounce back and be recondensed into the liquid. And in that case, it's a bit more complicated because you have to think about how are these molecules distributed in the gas surrounding the liquid. And this might not necessarily just scale with the interface area. So this is the sort of thing we want to look at. And the way we're varying the interface area is through changing the contact angle. So for 90 degrees contact angle, you have a minimum area. And then as it gets flatter or becomes more round, your area will increase. And for the kinetic evaporation case, you'd expect the evaporation rate to increase. And what we want to look at is this the same for diffusive evaporation? And then the next part involving complex geometry is that if we add in walls in places, you're blocking the diffusion of the vapor. So in this case, if you put it in a completely closed system, you'll get a point where the evaporation stops. So what we're doing is, okay, not completely closing the system, but we're going to look at implementing walls and seeing if we can sort of confine the vapor within the solid geometry. And then the last point, just to add on this, is that we do have reason to believe that for diffusive evaporation, the evaporation rate behavior might be more complicated than just scaling with the area because of this effect where if you have a wetting droplet, you'll find that the evaporation flux is not actually uniform across the surface of the droplet. So you tend to get much higher evaporation in the corners, which is what these arrows are showing. Basically because the molecules coming off at the edge can see less area of the droplet, so there's less probability of them being recondensed, basically. Okay, now we have the background. I'm just going to show the sort of system we decided on. We tried to keep this simple to just look at, okay, we have this confined geometry that's keeping the vapor in and looking at the different heights of this liquid in the geometry and then seeing how that affects the evaporation rate. So this plot is showing on the left-hand side, we have the liquid. In the middle, this is showing essentially the concentration fraction of the vapor and the gas. And then on the right-hand side, kind of hard to see, but this is the flux, the evaporation flux. And maybe you can see that this color is brighter in the corner, which is showing that effect that I showed on the previous slide. Okay, so now I will just briefly talk about the method that we're using. So obviously we have a Navier-Stokes equation, but we have a body force essentially included in this, which is representing the surface tension, and this depends on some chemical potential. I'll explain later. Then we have an advection diffusion equation for the concentration of the vapor within the gas phase. So that's what this YV in the advection diffusion equation is calculating. And then we have a Cahn-Hilliard equation for the phase separation with an extra source term. So that's what this mass sink term is. And this basically just allows the exchange of mass between each of the different fluids. And this depends, if you look at the expression on the bottom, depends basically on the gradient of concentration of vapor away from the interface, which is in the diffusion limited case. Yeah, it just depends on the gradient of vapor away, how quickly you can diffuse and evaporate. So yeah, I mentioned the chemical potential. We're just using like a double well potential. So this is pretty standard where you have these two minima, which represent the two independent fluid phases, which goes into this chemical potential in the middle of the slide. And then because obviously if you calculate the flux, you get sort of a flux per unit area. We generalize it into like a flux per unit volume across the interface by exploiting the fact that you integrate the concentration gradient within a cell, you get some fraction of the area. And if you do that across the whole interface, then you get the rate per unit area, basically. And then finally, something to mention, one of the reasons we kind of went with the phase field LBM for this evaporation approach is we've been using this model by Tai-Hun Lee, which basically reduces the spurious velocities to machine precision. So this is showing the kinetic energy actually, but you get spurious velocities falling with time until they basically flatten out. And this basically helps to improve the stability of the simulations and the accuracy of results. And this model can also handle high density and viscosity ratios. So I'll just show a quick validation test I've done. So I think this is similar to the validation test we saw earlier, but you basically have a liquid, a flat interface of liquid, and then a gas next to it. And on the end of the gas, there's a fixed value of the concentration fraction. And there's a higher concentration fraction on the liquid interface. So you have a gradient in concentration, which leads to the evaporation. And then for diffusive evaporation, you also expect that the molecules coming off the surface will add some velocity. So that's what this Stefan flow is showing. You get some convection off of the interface. So that's included in these analytical results. So the black dots are showing the theory, and then the other results are showing, as I run the simulation for longer, it should converge towards the theory with different resolutions. And you can see as I increase the resolution, it converges towards the theory. And this is showing the error percentage. And you see at the top end, it goes to below 1%. So we were able to reproduce the theory pretty well with this approach. Okay, now some results with this method. So we started looking at this geometry I talked about earlier. And as I mentioned earlier, for the kinetic driven evaporation, you expect as you change the area through the contact angle, you'd expect different evaporation rates as you get away from 90 degrees contact angle. But for this case, this is showing the essentially total flux for a given height of the interface. No matter what the contact angle is, it actually doesn't matter what contact angle you choose. So there seems to be no effect of the surface area of the liquid. And the way we're sort of thinking about interpreting this is that the walls are sort of confining the vapor. So there's a bottleneck at the top of the walls. So these lines are showing constant like contours of the vapor concentration. And if you look at the high contact angle case, you can see that it's not quite following the interface shape. So there's a lot more concentration near the contact line. And this is slowing down the evaporation there. So you don't quite get a uniform evaporation rate all across. And it seems like this cancels out the increase in area effect, essentially. And something further to show this is here I'm plotting, the red line is showing the interface, and the black line, I'm essentially plotting the concentration fraction along the black line. And if this was flat for each contact angle, then you'd expect the area to be having an effect. You can see it varies quite significantly for 30 and 150 degrees across this line, across the interface. So for 30 degrees, there's a much higher vapor concentration fraction just above the interface in the center, which means it's harder for more vapor to diffuse there and for more evaporation to happen, basically. And now what we're sort of looking at is, we've seen no effect on the evaporation rate with different contact angles, but can we manipulate the vapor profile to get an effect, and how can we design the geometries where contact angles can be a parameter you can play with to affect the evaporation rate? So this is just one test where we're essentially squashing the top boundary so that now the vapor concentration profile isn't just determined by the interface shape, but it's sort of squashed by the top boundary. And here we start to see differences in the contact angle, in the evaporation rate with contact angle. And the same sort of thing where now we wanted to do this with, think about the way we could design the surfaces. So it's not just artificially moving the boundary. Here we've added a cap to the posts. And you see that towards the top, this cap is sort of controlling the shape of the vapor profile. So you get separations with different contact angles. And then as it falls down, as the height decreases, they start to converge again, and you get the same trend that I showed earlier. And finally, I'll just talk about some future work we're doing. So I mentioned we wanted to look at carbon capture. So this is looking at this sort of mesh geometry. And now we want to see if these results are the same on these sort of double mesh layer surfaces. And then the next thing is also adding in some convective flow to see if we can, if there's a dependence on the velocity of flow on the effect that contact angle has on evaporation. Yeah, but that's everything. Thank you.
May I ask you a question about the Gaussian equation? So can you go back to the convection diffusion equation in the very beginning? Yeah.
Yeah.
The convection diffusion equation. Do you solve this equation in the whole system or just in the gas phase?
Just in the gas phase. Yeah.
So how do you deal with the boundary condition at the liquid gas interface?
So we use like an interpolated Dirichlet boundary condition.
Interpolation, why?
Yeah, on the interface.
Why don't you do it in the whole system?
We only do it in the gas.
Why?
Because you have to, well, we couldn't solve the, yeah, it's like separated. Yeah.
You said we move the top boundary closer to the pore, you see the effect of tangent angle, right?
Mhm.
And do you know the critical distance between the top and pore? So on which distance tangent angle will play an effect, and on which do you know the critical distance?
Yeah, so I'm kind of in the process of trying to find the distance where this has an effect. Yeah, so I don't know exactly yet, but it seems to be like pretty close. Like you have to move the top right. Obviously, this is artificial. It's kind of hard to do this in reality, but yeah, it's what really matters is the concentration profile right at the interface. So this boundary has to be like comparable to the size. The height has to be like comparable to the size of the interface, basically.
So how do you define the location of the liquid gas interface? Because it's a diffuse interface, right? So I'm a bit confused about how to do the interpolation.
Yeah, so the distance is based on just assuming a tangent profile.
Yes.
Yeah. So for like the halfway point at 0.5 in the profile.
At the level.
Yeah, because we have a diffuse interface, so we can know like the normal at any point to the interface, and then basically track that back, assuming like a tangent profile. Like there's probably more accurate ways to do this to find the distance, but it's sort of this is why we wanted to do these convergence tests to see what kind of error we get. Like the error here is basically to do with the.
I think it's like the first order, I think, if you go back.
Yeah.
Yeah, this case.
Yeah. But yeah, like there are better ways to do the interpolation interface. It's just the ways we sort of found would massively slow down the simulations. So this is sort of what we settled on.
The last question from my side. You said that you track the humidity also with the reflection diffusion. Did you get that? How do you know what's the value for the humidity?
So yeah, so for diffusive evaporation, we're basically assuming that like on the interface it's completely saturated with vapor because it's not limited, like it's always instantly refilled basically, because we assume it like evaporates really quickly compared to the rate that diffusion can happen. So that gives a boundary condition for the humidity, and then there's some expression you can get to relate that to like real parameters. And then the other end is just like you set some boundary condition. We just use a Dirichlet condition, but we're looking at tests where you have like convective flow, and then you can just allow the vapor to come off the interface and basically leave from another boundary, basically. But yeah, it basically just comes from assuming the concentration on the interface is the saturation value.
Okay, then thank you again. Speaker of the session is Chen Rangxi, who is talking about
So I'm Qin Guang. I'm from Helmholtz Institute, Erlangen-Nürnberg. I work with Professor Jens Harting. So my talk is about evaporation-driven particle deposition on substrate. So I'm go beyond a little bit the previous talk. I will couple the fluid with particle and study the evaporation-driven deposition on such suspension systems. So our institute is currently focused on renewable energy, so the solar cells and electrolyzers. And to fabricate such solar cells and electrolyzers, inkjet printing or blade coating techniques are often used. For example, for the solar cells, they can print the functional layers of solar cells. So we use inkjet printing or blade coating. Also, for example, for these electrolyzers, so there are different layers for these electrolyzers. The catalyst layer can be also fabricated by printing. So it's very simple and fast fabrication process. But the process of printing and coating need to be well understood so that we can get the optimal functionality of the materials. And in inkjet printing and coating, the basic form of drying suspension is drying of droplet or drying films. But after drying of the solvents, the functional materials are deposited on the substrate and with some defect. For example, this is a well-known coffee stain effect. So after drying a coffee drop on the table, for example, you can see at the edge of the deposit, there are more particles accumulated there. This is driven by capillary flow inside the droplet. Also by drying of film, there can be some pinholes on the substrate. So to understand this process, we need to gain insights into hydrodynamic flow or particle substrate interactions and the friction between particle and substrate, also the capillary interaction between particles, as well as the DLVO interactions. And we use light Boltzmann simulation to investigate these systems. We use so it's very simple BGK clearing operator with D3Q19 lattice, and we use the good old Shenzhen interaction model, and we also recently developed evaporation model in Shenzhen interaction model. So the evaporation in our case is diffusion dominated. And we couple the fluid with particles, just following the approach outlined. So there's more momentum exchange between fluid and solid particles. We solve Newton equations for those particles. And we also can implement the particle-particle interactions straightforwardly in this model. So here's a short movie to show the evaporation of suspended droplet. Just to show it works, and we also compare the radius of the droplet with the D2 law. It agrees also quite well with the theoretical prediction. And now, so I show you this case. So evaporation of a colloidal dispersion droplet. First, I want to place movie to show you the process. Yeah. Okay. The solvent is evaporating, and the particles are driven by the flow inside the droplet and surface of the droplet to move to the edge. Here you can already see the coffer rings effect. So more particles are deposited on the edge of the droplet. And for drying of this droplet, Popov, so he developed a theoretical model to describe the flow field inside the droplet, and especially at the end lifetime of the droplet, there will be a diverging capillary flow inside the droplet. So you see here, this is the velocity. This is the velocity near substrate inside the droplet as a function of time. So when you see near the end of the lifetime of the droplet, the velocity diverges. And one experimental group in Twente, they did a nice experiment. They used camera to observe the particle motion, and they found also the experimental results agrees very well with the theoretical prediction. And then we simulated the system and plot out the velocity radial velocity in our simulations, we also found a very good agreement between our simulation result and theoretical prediction on the velocity profile. So I show that we can reproduce the formation of the Coffin sting effect by drawing a colloidal suspension on a substrate. Also, radial velocity is in good agreement with experiments and theory. And then we can move forward. And we study the effect, the particle substrate friction force. So we just implement a constant friction force between the particle and substrate. And we increase the friction. So in the beginning, when with zero friction force, we see there's a dot-like pattern left on the substrate. So no Coffin sting effect. In this case, the particles can move freely, driven by the capillary force to the center, so they form a dot-like deposit. After we increase the friction force, we see a string-like deposit on the substrate. And we also try to develop a simple theoretical model to predict the average radius of the deposit after drying. And this is, we place the balance of capillary force and the friction force at the edge of the droplet, also at the counter line on the droplet. So the capillary force is a function of surface tension and particle radius and also counter angle of the substrate. And the friction force we set is constant, so we can, with the balance, we can determine the average radius of the deposit. So here we plot out our theoretical model with solid line. We see also a very good agreement between the simulation result and the theoretical prediction. And then we moved to the case of drawing a thin colloidal dispersion film. This case is quite relevant for printing our solar cells, because for solar cells, for some layers, they want to have very thin and homogeneous deposit. So in this case, we have dilute suspension, so a few particles dispersed in the solvent, and we also only model the spherical particles. And we studied the effect of substrate angle on the deposition pattern. In this case, I have 90-degree angle on the particles, and the substrate has 30 degrees. So it's a hydrophilic. We can consider it as hydrophilic substrate, and we allow the solvent drying. So this is a top view of the simulation system. The white dots are particles. Sorry. Oh, no. Yeah, it's nice in display. The solvent drying, and at some point the solvent will, the contact line will attach at the particles, and then dividing will happen. So then a particle deform the interface. This will generate a capillary force. Capillary drive the particle to accumulate into some structures. So this is for the lower contact angle case. Yeah, and we played around with the particle volume fractions. So we increase the particle volume fraction. We see how much area is covered by the particles. And if we assume the particles are uniformly distributed on the substrate, and it is only monolayer, then we can just simply predict the surface coverage fraction. It's just the number of particles times the cross section on the particles, and divided by the total area of the substrate. But so this is the simple theoretical formula. So this H0 is the initial film height, and particle volume fraction is the CV. So we can get the total. We can get the number of particles through this relationship. Then, but there's a maximum surface coverage of the random origin of spheres in 2D. So it's 0.77. This is the maximum surface coverage for of spheres in 2D. So we have a cutoff. So you see here, this the solid line is the simple theory equal to 23. And then I change the counter angle of the substrate from 30 degree to 150 degree. So for the lower counter angle and the also intermediate counter angle, we see a good agreement between the simulation result and the theory. So here you see the surface coverage increases linearly with particle volume fraction. But if we have a higher substrate counter angle, 150 degree, you see the deviation is quite large. So what happens with larger surface, with larger substrate counter angle? I will show you in the next slide. Here, this is for the case of higher substrate counter angle. The counter angle of the particle is 90 degrees still, but the substrate has 150 degree counter angle. This is solving the drawing. Also, dividing happens. And here we see the spherical droplet formed at the substrate. This is due to a strong repulsion between the substrate and the droplet due to the effect of higher counter angle. So in this case, the theory will fail. Then we want to improve the theory. Extend the theory for this case. So in the initial phase now, we just assume that after dividing a single spherical suspension droplet formed on the substrate. And then we also know the point of dividing is when the counter line is pinned on the particles. So that's why we know the total volume of the solution before dividing. We can calculate the radius of this droplet. And the droplet will also keep drying in a constant angle mode. And so we can, then I get this formula. This is the footprint of the droplet as function of the particle number. Also, this is the random packing fraction of 3D spheres, of sphere in 3D. And the theta is the counter angle of particles or substrate. It will be determined which counter angle is the minimum. Then plot out this equation 25. Here is the dashed line, and compare with the case of higher contact substrate angle. So I see also and the lower particle volume fraction, the theory also agrees with simulation result. But at a higher volume fraction, there's still division. Because I observed that at higher particle volume fraction, there are multiple droplets from the after divide. That's why our theory fails. Okay, then afterward we study the effect of a particle counter angle. So in the left plot, you see the case for particle angle, a particle counter angle equal to 90 degree, and then we reduce the particle counter angle to 46 degree. Then we run a simulation with different substrate counter angles. Now in this case, in the right plot, you see the surface coverage fraction is not dependent on the substrate counter angle anymore. So we see that a lower particle counter angle eliminates the effect of substrate counter angle. So in this also shows us even you have like the substrate has a very higher counter angle, but we can still get a homogeneous deposit of drying. Yeah. So I think experimentalists they will like this. So why? Because you see here, I show you a snapshot of simulation. This is a case with 150 degree substrate counter angle. You see the particles, the solvent lies at the particle surface, not on the substrate. You see, that's why the deposition pattern can be also homogeneous. So there's no droplet formed after dividing. So this is the reason. Yeah, so now I come to conclusions. I just showed you some cases, what we did with pseudo potential light border methods coupled with the discrete element method for particles. And here some snapshot for also other project, also ongoing project. So there's drawing of droplet with ellipsoidal particles. Also there's drawing of suspension droplet on a white film. as well as collision between two liquid lenses on fluid-fluid interfaces. Also, we move to study the evaporation of suspended droplet on porous substrate and also in the nozzle of inkjet printer. Thank you for your attention.
Questions?
So if I understand this right, you have particles both on the surface and inside the board.
Yes.
So exactly what this distribution is would in equilibrium would depend on your contact angle as
Yeah,
well.
depending on contact angle. If you
So
can.
the initial state, is that fully equilibrated or?
No, means initially we randomly distribute the particles on the inside droplet and the surface.
So do you think that will make a difference if you let it equilibrate first?
If you include first, so the particle will, for example, will accumulate all at the interface. If the particle contact angle is has 90-degree, right? So and this will have effect on the evaporation rate also, right? The particle will block the interface, so prevent evaporating. Yeah. But so far we don't consider this effect yet. We just random distribute and evaporate immediately. Yeah.
Yeah, that could have a big effect on
Sure.
exactly how they're distributed.
Yeah.
Or the configuration, yeah.
Yeah. Thank you. Yeah.
I have a small question on method. So what is the density ratio? So
Of between two, we use two components. The density, two components. No, two components. Yeah.
So what is the density ratio between the solid and the?
Between the solid, between the two, between particle.
Between the particle and the liquid phase.
Oh, we give the particle just density 2, I think, and liquid density 1. Yeah.
Density ratio 2.
Yeah, that's
Okay.
it.
And what is the typical size of the particles in that?
In large units, we use, I think, 6, around 6. No, radius around 6. Yeah, I think so. Yeah.
And what is the computational domain size for your 3D simulation?
3D, we have 150, 512, so around. Yeah. Okay.
Okay, nice work. So my question is that in the community, some people don't explicitly simulate the particle, but they actually couple with another equation, maybe an infection diffusion equation.
Yeah.
So clearly at the very end, when you get this complicated symmetry breaking, you will completely miss that if you just do infection diffusion. But I'm just wondering at the very beginning, can you say a little bit when actually this sort of approach that doesn't explicitly model the particle will break down? Do you have some idea where your method will really shine in the sense that you can't just take an average quantity?
I think when particle interaction play an important role in the simulation, right? In the system, then normally convection or diffusion you cannot consider the particle interactions. Also, the capillary force between particles is also important.
So that's essentially then when I guess the particle separation becomes.
Yeah, depend. Yeah.
It's not very.
Yes, I think so. Yeah.
Could you say something more about this nozzle blocking?
Yeah. So that's means by inkjet printer, when it is not printing, it's just left there. Then from the nozzle open, right? And the solvent will keep evaporating, and this will drive the particles accumulate at the nozzle end, and then the particle could keep accumulating. This will block the nozzle. So when they print again, they need to add a pressure pulse to print to.
So it's not about the substrate, but the.
Yeah. Yeah.
Any more questions?
Yeah, another question.
Yeah.
How about the mass conservation in your method?
I
think you need some interpolation.
In boundary, we don't do interpolation. It's total, like mass totally conserved, because we impose a constant density at the boundary. So it's the transition method has this like diffusion in the nature.
How do you treat the viewpoint?
We convert it to another component.
Okay.
Yeah, in this way. We keep total mass conserved. Yeah.
I think we are doing a very similar simulation, but we use single component superpotential.
Yeah.
With this discrete element.
Okay, nice. Yeah.
Okay, with that, I would like to close the session. Time for lunch.
Thank you.
Thank you.